Okay, here it is. It says 5 cyclists are in a circular track, separated 3 meters from each others, from each one of them. Okay, they run 5/6 of a rep in 55 seconds. Okay, so the first question, what is the angular displacement? Letter B, what is the angular velocity? And letter C, what is the distance traveled? So let's do this problem. Okay, I'm going to return here because I'm gonna make the drawing. Okay, so the first drawing that I'm gonna make is the circular track. Okay, because they are in a circular track. So imagine that this is the track. Well, imagine that is a circle. Okay, this is the center. Okay, and this line over here, is the start line. Okay, the start. Okay, so the cyclists are separated by 3 meters from each other. So I got the first one, 2, 3, 4, and 5. Okay, so between them, this is a separation of 3 meters, 3 meters, 3 meters, and 3 meters. Okay, so this is the cyclist 1, 2, 3, 4, and 5. Okay, now the distance from the center to the first cyclist, I'm gonna say that that distance is 5 meters. Okay, it's gonna be different. 5 meters. So this distance is 5, this is 3, 3, 3, 3. Okay, and also the problem says that they run 5/6 of a rep. So that means that they didn't complete the full circle of the track. Okay, so they just travel, I don't know, they just got here. Okay, so that is the goal line. Okay, so this is the first cyclist, 1, 2, 3, 4, and 5. Okay, and they travel the same distance, the same angular displacement at at the same time. They all of them reach the goal in 55 seconds. You might think that that is not possible, but let's imagine that they did something like this. Imagine that this is the goal. Okay, so if you see all these people reach the goal at the same time, I repeat, they reach the goal at the same time. Okay, so let's find the answers. Okay, so the first question is, what is the angular displacement? Okay, remember that the angular displacement, well, is kind of the angle. Yeah, it's the angle that they travel, but measure in radians. Okay, this is the angular displacement over here. Okay, this is the angular displacement, and we already know that data because they say they run 5/6 of a rep in 55 seconds. Okay, so that means, for example, we all know that one rep is 360 degrees. Okay, so how much is 5/6 of a rep? Okay, so the only thing that you need to do is, for example, you got 360 and you're going to multiply this by 5/6 and you're going to find the degrees. Okay, so the angular displacement is 300 degrees, yes, but I need to transform those 300 degrees into radians. So let's do it. So I'm going to have this formula: 300 degrees over 180 degrees equals x over p. I'm using the equation, the formula that I just wrote to you. This one over here, okay? I got degrees, so I write degrees. And x, well, I don't have radians, but I need to find them. That's why I use x. Okay, so let's find how many radians. So x equals 300 p over 180. So let's do it in the calculator. Okay, so fraction 300 p over 180. Okay, so how much is that? Okay, those are the radians. That is the angular displacement. So I'm gonna save this value in my memory A of my calculator, and I'm gonna write over here that the angular displacement equals 5.23 59 radians. Okay, I'm gonna circle this. This is letter A, and I also have got this value saved in my memory A of my calculator. Now if we return to the video, just see that all of them travel the same angle, okay, the same angle. Okay, so we're not going to find a different angular displacement for each one of the cyclists. Okay, all of them are going to have the same angular displacement. Now letter B, what is the angular velocity? Okay, so the formula for angular velocity is angular velocity equals the angular displacement over time. Okay, so the time, I already got it, is 55 seconds. So I'm just going to divide this value that I just found, angular displacement, over 55. So fraction alpha A over 55, and that is the angular velocity. Okay, how many radians these persons travel in 1 second. Okay, so angular displacement equals 0.0951 radians per second. Okay, so this is the answer. I'm gonna save this value in my memory B, shift STOB. Okay, so this is B, and I got this value in my memory B. Okay, and then what is the distance travel? Okay, in order to find the distance travel, I need to watch over here this equation, and in here S means the distance. Okay, so I'm gonna erase this one over here. Yes, I'm gonna erase it, and I'm going to isolate S. So distance equals the angular displacement times the radius. Okay, so with this equation over here, I'm going to find the distance, but I need the radius. So if you see, guys, well, I'm going to have different radius for each one of the distances, sorry, for each one of the cyclists. So if I want to find the distance, I'm gonna find it over here. If I want to find the distance for the first cyclist, okay, so the equation will be distance 1 equals, well, the angular displacement, all of them got the same angular displacement because all of them travel the same angle, degrees, and times the radius 1. Okay, so in this case the radius 1 is 5 meters. So what I'm going to do is going to multiply 5 times the value of the angular displacement that I got it saved in A. So that is the distance of the first person, of the first cyclist, 26.1799 meters. Okay, so I need to find the distance travel by each one of them, because if you see here again in the video, so if you see here, the person that is at the center is not traveling the same distance as the person that is at the end of the line. If you see, the person that is at the end needs to travel more distance than the person in the center. So the further, according to this formula, the further you are from the center, the more distance you're gonna travel. And you can see it over here. For example, the distance traveled for the cyclist 1 is this. This is the distance, or this is the trajectory, okay? And the trajectory of the third cyclist is this one. So if you see, the trajectory is greater as you get further from the center, okay? So let's find the distances. So the distance of the second cyclist is going to be 5 plus 3, so it's going to be 8a. Okay, because the first distance is 5 meters, and then plus the distance from between the first cyclist and the second cyclist. So how much is that? Okay, 41.88. 41.88 meters. Okay, as 3. So I got 8 plus 3, 8, 9, 10, 11. Oh, so it's going to be 11 alpha A. So it's going to be more, 57.59 meters. Okay. Now the other one is going to be 14A. The S4, the distance 4. Okay, so this is 4, it's going to be 73.30 meters. And finally, the distance traveled by the cyclist, the fifth cyclist, so it's going to be 17. Okay, yes, no, it's not going to be 17. 3 times 12, yeah, it's going to be 17 times alpha A equals 89.01 17 meters. Okay, so again, if you see, all of them reach the same goal at the same time, and all of them travel with the same angular velocity. But if you see, the distances were different. So here we're gonna see another concepts. Okay, the circular concepts are going to be exactly the same for each one of them. When I say circular concepts, I'm referring to the angular displacement and the angular velocity, but not the linear concept. So for example, we're going to have a new concept over here that is called the tangential velocity. Okay, tangential velocity, this one over here. Okay, what is the tangential velocity? Okay, if you can see over here, this video, okay, that's the linear velocity according to the distance from the center. Okay, so for example, let's return to this drawing over here. Okay, so the tangential velocity is a linear velocity. So imagine that you got a stone. This is a stone and this is a rope, and you are spinning that rope and including the stone. So in a moment, the stone is going to be let go. It's going to get free. So once that happens, that stone is going to have a tangential velocity, something like this. Okay, if the stone is let go, okay, the velocity of the stone is going to be the tangential velocity. Of course, if the stone is not attached anymore to the rope, this stone is not going to have a motion like this. Okay, it's not going to continue with that kind of motion. Okay, no, it's free. Now that it's free, it is going in a linear motion. Okay, so if you see, this person over here is going to have a tangential velocity, and this person over here is going to have a different tangential velocity. Okay, so that is going to answer our question in why Do they travel the same angular velocity with the same angular displacement with the same angular velocity, and they reach at the same time? But of course, the person that is further needs to go with more velocity. It's going to it needs more effort to fulfill that goal. Okay, so that answer can be answered using the concept of tangential velocity. So tangential velocity, I'm gonna write it over here. Tangential velocity. Okay, velocity. Okay, this, if you want to call it, this is linear velocity. Okay, linear, the velocity in a line. Okay, so tangential velocity, we can define it like this. And before I write the equation, it is important to mention that this tangential velocity must be perpendicular to the radius. So this is very important. Okay, this signal over here means perpendicular, and remember that perpendicular means 90 degrees. Okay, so the tangential velocity equals, remember that this is a linear motion. Okay, linear velocity. So if we go back to this equation over here, this is the angular displacement, and the angular displacement equals the distance traveled linear over radius. Okay, so the tangential velocity will be the distance traveled over time. That's very easy. Distance over time. Okay, but I'm talking about this distance over here. Okay, this distance over here, that distance. Okay, oops, yes, that distance. Okay, so if you see, if we divide each one of them, for example, this distance 26.1799 5a. Okay, that's that distance, 26.1799 over 55, that is the time. Okay, that is the velocity in meters per second. Okay, this is the tangential velocity in meters per second. So if I got this one, 41.88 divided by 55, well, I'm gonna have, this is the tangential velocity measured in meters per second. Okay, but right now I'm not gonna find them because I'm going to continue with this equation, and that will be the end of the video. Okay, so this is what about the units? So this could be meters or centimeters or kilometers or miles. It's up to you. And time, well, it could be seconds, minutes, hours, days. Okay, it's up to you. Okay, so this is the equation number 3. This is the equation number 3, and the units for tangential velocity, well, most of the times are going to be meters per second or kilometers per hour or RPMs. Well, no, RPMs is for another one. Sorry, meters per second, kilometers per hour, miles per hour. Okay, I hope you understand. You got the idea. Miles per hour. Okay, so then, okay, so that is the third equation, but that equation could be written as follow. Okay, so tangential velocity equals s. So what is s? If you see, I got it over here. S is distance equals to angular displacement times the radius over time. So with another color, if you see, I got angular displacement over time. I'm gonna circle these two. Okay, so the angular displacement, okay, if you see, I got it here. Angular displacement over time equals the angular velocity. So the other equation that we are going to use for tangential velocity, and is really one of the most important that we are going to use on this topic is that one. Tangential velocity equals the angular velocity that multiplies the radius. Okay, so I'm gonna circle this equation. This is gonna be the formula, the equation that we're going to see, and the units, well, remember that the units are gonna be exactly the same. Okay, the units are gonna be, it could be meters per second or kilometers per hour. It's up to you because it's a linear velocity. So if you see with this equation, the tangential velocity is going to depend on the angular velocity. In this problem, we already got the angular velocity that is going to be the same for each one of them. Okay, if you see, it's gonna be the same for each one of them because all of them travel the same angle. And for example, the tangential velocity, okay, the angular displacement times the radius. Okay, so the radius is the only one that is going to be different from each one of them. So that means that all the cyclists are gonna have different tangential velocity, and that is going to prove why this guy over here is going to have more effort in order to get at the same goal. Okay, so guys, I recommend you to find the tangential velocity for each one of them, and in the next video we're going to finish explaining this uniform circular motion, and then we're going to see more problems about this topic. Okay, well, see you guys. Bye bye.